Oops, I cancelled it. I'm sorry. This one. Oh, there is someone else who's operating. Good. Am I audible? Okay.
Speaker is Yeshwant.
He will just a second. I think the animations are not working here. Oh, I've submitted PPT. Okay. Which one? Okay. Oh, okay, okay. Sorry, sorry. Okay, shall I start?
So our next speaker is Yeshwant. He will talk about EFX allocations on some multi-graph classes.
Thanks, Sham. Hello, everyone, and thanks for coming. So I'll be presenting our work, EFX allocations on some multigraph classes. This is joint work with my advisor, Umang Bhaskar. So let me start by defining the general problem that we are attempting at, and then we'll go to the specific problem that we attempted. So the general problem is called discrete fair division problem. So in this, we are given a set of agents, a set of indivisible items. Each agent has a value for every subset of items. For example, the first agent has value 10 for that subset, the subset containing cell phone and bicycle. The second agent has value 15 and so on. And the goal is to allocate these items fairly among the agents. Okay. So formally, we are given a set M of indivisible items, a set N of agents. Each agent I has a valuation function which takes a subset of items and gives out a value. An allocation is an N partition of the set of items M. And the goal is to allocate these items fairly among the agents. Okay. Now, to measure fairness of an allocation, various fairness notions have been studied in the literature. Popular among them are NV freeness, equitability, proportionality, etc. We'll be focusing only on NV freeness in this talk. Okay, so before I define NV freeness, let me introduce you to two commonly encountered valuation functions. The first one is additive valuation. So it says a valuation B is additive if for any subset X of items, the value of that subset X is sum of the values of items in it. A more general valuation function called monotone non-decreasing valuation, also known as monotone goods. So it says that if you give me a subset S, and if I keep adding items to it, the value either increases or remains the same, but it doesn't decrease. Okay. And so that's why we call it as monotone goods. So these are positively valued items. So throughout this talk, we'll assume that the valuations are monotone. And wherever I'm assuming additivity, I'll mention that in the slide. Okay, so coming back to NV freeness, so an allocation is NV free if each agent prefers his own bundle over any other agent's bundle. So formally, for any pair of agents I and j, Vi ai is greater than or equal to Vi aj, where ai is the bundle that agent I has and aj is the bundle that agent j has. So let's understand this definition by an example. So suppose, so I'm assuming additivity in this example. So suppose we have two agents and three goods, and these are the values that the agents have for the items, for the goods. Okay, so now consider the allocation where agent 1 gets item G1 and agent 2 gets G2 and G3. Now this is an NV-free allocation because agent 1 has value 20 for his bundle, and his value for agent 2's bundle is 5 plus 5, which is 10. So he prefers his own bundle over agent 2's bundle. And similarly, agent 2 also prefers his own bundle over agent 1's bundle. So this is an NV-free allocation, but the bad news is that NV-free allocations may not always exist. So consider two agents and one item, and both of them evaluate positively. And if we give it to one agent, the other agent would envy. Okay, so so now the thing is, like, I mean, this motivates us to look at basically nearly envy-free allocations. So one of the relaxations of envy-freeness is what we call as EFX, also known as envy-freeness up to any item. So basically it says that you allow envy in an allocation, but that envy can be eliminated by removing any item from the envied agents bundle. So here if agent I envies agent J, then you can remove any item from agent J's bundle. Sorry, the envy would get eliminated. Okay. So consider an instance again with two agents and three items, and this allocation where agent 1 gets G1 and agent 2 gets G2 and G3. So in this allocation, agent 2 doesn't envy agent 1 because its value is 10 for his bundle, and for agent's 1 bundle is 10. Okay, but agent 1 envies agent 2. However, this envy can be eliminated by removing any item from the agent 2's bundle. Okay. And this is hypothetical removal of an item. We are not actually removing an item. We are just assuming that if this item is removed, then the envy should get eliminated. Okay, so now the question is, do envy-free allocations exist? Okay. All right. So researchers have put significant efforts in solving this problem, and they have been successful in solving this problem for some special cases. So these are the special cases for which EFX exists. So I'm going to talk about the last one, which is the latest and the current best known result. So it says that if assume that we have many, like any number of agents, but they can only have these possible additive valuations. So let's say we have 4 agents, okay? 2 of them, let's say, take VA, this agent takes VB, and this takes VC. And this VA, VB, VC are additive valuations. Then in that case, EFX always exists. Okay, so basically for 3 agents, we know EFX allocations exist, but beyond that, we don't know. So it's a enigmatic open question, basically. Okay, so people have looked at many restricted valuations. So one such valuation is called graphical valuation. So these were introduced by Christodoulou and others in their EC paper. So this says that an instance can be specified as an undirected graph, okay, where vertices are agents and edges are items. So for example, over here, vertices 1, 2, and 3 are agents, and edges 1, 2, 2, 3, and 1, 3 are items. Okay, and the additional assumption is that each vertex I values its incident edges positively, and its value for any edge that is not incident to it is 0. Okay, so under these assumptions, let us look at an example of an EFX allocation. So consider this instance where the edge weights represent the values that the vertices have for the edges. For example, edge 1, 2 has value 10 for vertices 1 and 2. This edge 2, 4 has value 5 for 2 and 4, and so on. And I'm assuming additivity again here. Okay. So if you consider this allocation, this is an EFX allocation. So the arrow head over here represents, it indicates that agent 1 has received this edge. Okay. So edge 1, 2 is given to agent 1. Edge 2, 4 is assigned to agent 2, and so on. However, this edge 1, 3 is not assigned, it is not assigned to either of its endpoints, but it is assigned to agent 4. And since every vertex over here receives exactly one edge, this is an EFX allocation.
Here, the agent has the same value.
No. The 2 endpoints have the same value.
Right.
Yeah. Okay, I hope this is clear. 2 agents, yes. So each edge will be valued positively only by the endpoints, and it will have value 0 for any other end. Which one? So these are the values that so for example, if you consider this edge 1, 2, so vertex 1 has value 10 for this edge, and vertex 2 also has value 10 for this edge. 0 for all others. Okay. Sorry? In general, it will not be symmetric. So agent I can have value, sorry, vertex 1 can have value 10, vertex 2 can have value 15, let's say, for the same edge. Okay, for simplicity, I have assumed symmetric valuations here. Okay, so for simple graphs with monotone valuations, we know EFX allocations always exist. This result is due to Christodoulou and others. Now we want to answer the existence of EFX. We want to answer this question whether EFX exists in multigraph instances. So here an instance is specified as a multigraph. So instead of having a single edge, you can have multiple edges between any pair of vertices. And the question that we want to ask is, do EFX allocations exist or not? So we could partially answer this question. And we showed that for bipartite multigraphs with cancelable valuations, EFX allocations always exist and can be computed in polytime. We also showed that EFX allocations exist for tree multigraphs with monotone valuations, and for T chromatic multigraphs with girth at least 2T minus 1, they exist. So in this talk, I'll be proving the first result, and I also assume that the valuations are additive for simplicity. Okay. I'll skip this slide in the interest of time, and I'll come back to it later if we have more time. Okay, so this is a theorem that we are planning to prove. So EFX allocations always exist in bipartite multigraphs with additive valuations, and they can be computed in polytime. So the technique that we use is called cut and choose. So let's call the set of parallel edges between vertices I and j as Eij. Okay. So in this cut and choose technique, either I or j cuts the set of edges that is the set of parallel edges between them, okay, into two bundles. And the vertex who doesn't cut will get a chance to choose the one bundle among the two. Okay, so in this case, let's assume that j cuts or partitions Eij into two bundles, E1ij and E2ij. And these two bundles, E1ij and E2ij, satisfy certain property. They are basically EFX feasible for vertex j, meaning that if j gets the lesser valued bundle, let's say E2ij, okay, then it would envy the other bundle, that is E1ij, but this envy would be EFX. Okay, so even if j gets a lesser valued bundle, it doesn't mind because its envy towards the other agent who will receive E1ij would be EFX. Okay, so what we will do is we'll give vertex I its favorite among E1ij and E2ij, and the other will be given to agent j. Right, so I doesn't you are giving I the chance to choose the best among both. Okay, so I will never envy j. J may envy I, but that envy will be EFX. Yeah. Yeah. So now if you give something additional to vertex I, apart from E1ij, then j may strongly envy I. The envy won't be EFX. Okay, so this cut and choose basically runs in, this cut and choose protocol runs in polytime for cancelable valuations. So basically additive valuations is a subclass of cancelable valuations. So it runs in polytime for additive also, but for general case, it requires exponential number of value queries. All right, so let me state the algorithm for bipartite multigraphs. So the input is a bipartite multigraph with additive valuations. Output is an EFX allocation. So initially we'll start with an empty allocation. So let us label the set of, the vertices in L as 1 to up to cardinality of L. Then in any iteration I, we do the following. So you look at the neighbors of I. Okay, so here the neighbors of I are X, Y, and Z. So each neighbor will cut the corresponding multi-edge. For example, X will cut EIX, Y will cut EIY, and Z will cut EIZ into 2 bundles. Okay, and these 2 bundles will be EFX feasible for them, right? So basically, we'll have 6 bundles after each of these vertices cut the corresponding multi-edges. Okay, now suppose, I hope that even IY is visible in the slide. Okay, so suppose even IY is I's favorite among all 6 bundles. Okay, this is favorite for I among all 6 bundles. And if E2IY is favorite for Y, okay, then we can give this bundle to I and this bundle to Y. So since even IY is favorite among all 6 bundles, I doesn't mind giving E1IX to X and E1IZ to Z. Okay, so what we will do is X will get its favorite bundle, say E1IX. The other bundle goes to I. Y gets its favorite bundle, E2IY in this case. The other bundle goes to I. And E1IZ will go to Z and E2IZ will go to I. Okay. So in this allocation, like what is all these vertices, I, X, Y, Z, they have received their preferred bundles. Okay. So now let's consider the other case where Y's favorite bundle is also E1IY. Now both I and Y, they fight for E1IY. Okay. So in this case, we'll look at the preference of vertex I. Okay. So I doesn't mind giving E1IX to X. So we will give E1IX to X. Similarly, even IZ can go to Z. Okay. Now I will choose its best among E1IY and the union of these 3 bundles. Okay. So suppose if it prefers E1IY over these 3 bundles, then we will assign E1IY to I and the other 3 bundles will go to Y. Okay. But here there is a chance of having NV from vertex Y to vertex I. Okay. Right. But this NV would be EFX because remember these 2 bundles, right? E2IY and E1IY were EFX feasible for vertex Y. Okay. So since it has received this bundle, okay, any NV towards vertex I from Y would be EFX. And the other case is simple. Here basically vertex I prefers this union over E1IY. So it gets, so even IX as before it goes to X, even IZ goes to Z. And these 3 bundles go to I and even IY goes to Y. So in this allocation, no one will envy each other. Okay. So now let's look at the proof. So in this slide, like basically vertex Y is a favorite neighbor of I because this was the favorite bundle, right, for I among all 6 bundles. That is why we call vertex Y as a favorite neighbor of I. Okay. So the claim that we want to make is that at the end of any iteration I, the partial allocation that we obtain is EFX. And any NV, if it is present from, for example, for vertex R, if vertex R is envied, then it would be envied by its favorite neighbor only, and no other vertex would envy R. Okay. So let's prove this via induction on the number of iterations. So the base case is easy because initially the allocation was empty, so it is trivially EFX. So let's prove the induction step. Let A prime and A be the allocations before and after iteration I. So A prime is, I have highlighted it in blue and A is highlighted in orange. Okay. Now consider the case where basically vertex I prefers even IY over the union of these 3 bundles, which was the case where vertex Y envies vertex I, but that NV is EFX. Okay. So now these are the bundles like A prime X, A prime Y, and A prime Z are the bundles that these vertices had from the previous iteration, from the previous runs. Okay, and these are the current bundles. The orange ones are the current bundles. Okay. So basically, we can use additivity, and by induction hypothesis, we can say that vertices X, Y, Z, they do not envy each other. So I'll just prove that vertex X and Y, they do not envy each other. And the same thing holds for the other cases also. So look at vertex X. So it has received E1 IX, which it prefers over E2 IX. Okay, and its value for the other two bundles is 0 because these are irrelevant for vertex X. Okay, so it prefers E1 IX over E2 IX. Its value for other two bundles is 0. And by induction hypothesis, it preferred A prime X over A prime Y. Okay, so basically, if you consider the entire bundle, it prefers over the bundle of Y. So X doesn't envy Y, and similarly, Y also doesn't envy X. We can show that. Okay, so the only NV that is there in this allocation is from the new NV that got created is from vertex Y to vertex I, and that is EFX. Okay. And the other two cases are simple because everyone got their favorite bundles, so no one envied each other. And by induction hypothesis, they didn't envy each other in the in that allocation also. So the overall allocation is again EFX. Okay, so now so we showed that the allocation obtained by this algorithm is EFX. Now we want to show that this runs in polytime. Remember EFX 2 minutes. Okay. Remember that the cut and choose protocol runs in polytime for additive valuations. And all these operations can be done in polytime. Okay, so the overall algorithm runs in polytime. Okay, so for future work, yeah, so this question remains open. Does EFX exist for more than 3 agents? So let me define PQ family of instances. So a PQ family of instances is it is a set of instances where each good is relevant to at most P agents, and any pair of agents can share at most Q common relevant goods. Okay. So for example, if you substitute P as 2 and Q as 1, it represents a simple graph instance. Okay, for which we know EFX always exists. 2 comma infinity instance is a multigraph instance that we try to solve. Okay, so the question that we want to ask are like, does EFX exist for 2 comma infinity instances, that is multigraph instances, or in general P comma Q instances, or hypergraph instances? Okay, so in hypergraph instance, you are given a set system. Okay, so the hyper edge would be a item. Okay, and the vertices that are present in that would be the agents who will evaluate positively. Okay, for such instances, do EFX exist or not? So these are the open questions. Yeah, that's all from my side. Thanks.
So I had a question about the proof. When you give extra items to, let's say, X in some iteration, does it can also hurt the EFX NV from the agents before I, right, to X?
Yeah, so the key point here is that the NV, okay, at any point would be from a vertex in R to a vertex in L, because we always give a chance for the vertices in L to choose their best bundles. So any NV that is present in the allocation, in any partial allocation, will be from a vertex in R to a vertex in L. Okay, and since if you're talking about I's bundle from the previous iterations would be empty, because at any point of time, we are allocating the edges that are, so in iteration I, all the edges that are incident to I are allocated among I, X, Y, and Z. Okay, so it is allocated among I and its neighbors. Okay, so that is the reason I's previous bundle, like the bundle from previous iteration, would be empty. Okay, so any new NV would be from Y to I, that is its favorite neighbor too. Oh,
So if you had to give the items to agents only value it non-zero, right?
Mhm.
So you know that in general graphical valuations, it does not always exist, but
Right,
you're
right.
only looking at bipartite. Do you know anything strong?
So you're talking about orientations? Yeah, so orientations may not exist even in path, basically, multi-path.
Oh,
Yeah, so if you take this example, right? Let's say so no, I think this should be 5, I guess. Um, So there is only one edge between these two vertices. Okay, so let's say A, B, C, and D. So there is only one edge which has value 14 for both the endpoints. Okay, so you can either orient it in this direction or the other direction. Let's say if you orient this in this direction, this guy cannot get any item because otherwise the NV would be strong NV. So the only way you can orient these edges are in this direction. But now the NV from this agent to this agent would violate EFX property. So this is an example.
So let's thank the speaker.
Shusha,